Hello everyone, thank you for registering yourself for the Abacus Advanced Structural Engineering Training Program and joining us for today. So my name is Mayank Panchal and I am the founder of Pixo Learning. So the Pixo Learning company has been providing a top-notch higher educational services since 2017. Our primary focus is on offering our students online courses and the specialized training program and the services for the industry specific. With our digital learning platform, the college students and the working professionals can learn, train, and receive the project assistance and conduct research at the highest level. Assisting them in developing the necessary skills and preparing them for the workplace is something that we can be do. We are be offering for the videos based online courses and also the live certification training program for the specific different type of softwares based on the specific industries and the category like the civil, mechanical, aerospace and all other. In civil also we can be offering for the structural, geotech, highway, transportation and traffic management and some other categories that we are be working. We can be providing the complete project guidance and assistance on the Abacus, the AutoCAD, the ETABS, StatPro, ANSYS, and other type of the softwares. We can also check out the students' feedback from the Google reviews that we are be receiving from our online courses and the training program. So this is the short intro of the company that what we are be doing. Now it's time to introduce to you the today's training program host and Mr. Hisam Tariq and your educator also. So he is giving details of the training program about the Abacus Structural Engineering, the live training program. To highlight the things about the syllabus and what are the content that we are be providing. So these all other information that they can be provided to you. He has an experience of in the final animate analysis in the more than the 2.5 years. He has an expertise in the constitutive modeling, the linear and the non-linear FE simulations and the composite materials and many more. He completed the studies and do research work at IIT Kharagpur with the top-notch universities in India with a dual degree BTech in civil and MTech in the structural engineering. So these are the short intro about the Mr. Tariq, and I will invite you now so they can be handle this webinar now and give you intro about the our training program and other details also.
Thank you, Mank. Can you please unshare your screen?
Yes, sure. Yeah.
Mm. Can you see my screen?
Yes, yeah.
Okay. So actually, I should rather should I use this website for?
Yeah, definitely. Yeah.
Okay, fine. Then it's fine. So the course is about Abacus structural engineering. Most of the some of the topics of structural engineering will be discussed in this course, and it is for anyone who is maybe in the final year of their bachelor's or master's or enrolling in PhD. So the prerequisite for the course is you should have some basic knowledge of Abacus. That's it, and it is very important to learn abacus after learning finite element analysis. So you should also have some basic knowledge of finite element analysis, and I suggest while you take this course you learn finite element analysis side by side. Okay, so I'll quickly discuss the syllabus. So firstly we'll start with the behavior of material, mostly elastic materials and plastic materials, where our focus will be initially on concrete. They will be discussed, then maybe we'll discuss how brittle, quasi-brittle, and ductile materials fail, then stress strain curves of elastic and plastic materials, and then we'll move towards elasticity and plasticity of concrete, hardening, then yield surfaces, etc. So these will be the basics of the behavior of material that will help you to understand how we define the concrete damage plasticity model. So this model is in Abacus, which like helps you to simulate the behavior of concrete in Abacus. So this constitutive model is very famous and like very widely used throughout in the research community of structural engineering. So in this we'll study about the basics of CDP model, what are the parameters that are used to define how is the yield surface of concrete damage plasticity model, and those things. Then we have to study the behavior of concrete in tension and compression. For that we'll discuss some equations and how to plot or how to obtain the stress strain curve of concrete if you know the strength of the concrete. So there is slight difference for normal strength concrete and high strength concrete. So we discuss all these things, and then if you use CDP model, you may have convergence issues if you use Abacus standard. So that will also be demonstrated how to take care of that. Further, we'll apply the concepts learned here and in material behavior and CDP in a cantilever beam. So we'll model a cantilever beam, plain concrete cantilever beam. Then I'll discuss about mesh convergence study. Then there are two main solvers in Abacus: implicit, that is Abacus standard, and explicit. So I'll discuss the difference between them, how each solver solves the problem, and static analysis is done in standard and quasi-static in explicit. I'll discuss those things. And also, as I said, mesh convergence will also be illustrated. Then I'll teach about mesh biasing, that in some areas if you need fine mesh, how will you do that, and you can keep the coarser mesh near the areas which are not of interest to you in the beam. Similarly, the difference between the results in standard and explicit will be discussed, following how amply you have to define the load. You can define it instantaneously using a tabular amplitude or smooth step. Those things will be discussed here in this module. Following that, we'll go a little bit advanced where we'll just reinforce our concrete beam. So after reinforcing our concrete beam, we'll okay, there is some, I don't know, this has been copied twice. Anyway, Mayank, you should correct it. You should put the contents of RC and pre-stressed concrete beam here. Anyways, so here we'll discuss the how to give reinforcement to the concrete, embedded constraint, basics of steel as reinforcement. Then we'll go how to give pre-stress. You because in pre-stressed concrete you have to give pre-stress to your bars. So we'll also discuss that. And that is give you most commonly cooling method. There is a cooling method where you use thermal stress analysis. That's how pre-stress is given. So I'll discuss that in this module. Following that, we'll model a concrete column under compression, and then using a solid element, or if you have a circular column to improve the computational efficiency, we can also model using axisymmetric elements. So that will be demonstrated. And obviously axisymmetric elements, load should be axisymmetric, boundary conditions should be axisymmetric, and geometry should be axisymmetric. That will be demonstrated. Following that, I'll discuss how, if you are modeling a column and you want to compute the reaction forces, that I'll discuss. We have to use rigid body constraint for that. That will be discussed further. Displacement control loading will also be shown, because there are two types of loading. Either you apply a force somewhere. If force is applied, then say force is constant, acceleration is constant, velocity varies linearly with time, and displacement varies as a function of time, it is quadratically, right? But if you apply displacement control loading, then you are just varying displacement with respect to time. So there is a fundamental difference between the two types of loading that will also be discussed. Furthermore, we'll go with steel beam, and I'll also demonstrate some of this today. We'll model steel as elastic and then as plastic material, because it's a ductile material. Then what constitutive modeling models are used for steel, that will also be discussed. And in that, probably we'll discuss this today also: engineering and true stress strain, plastic strain, these things. And then this isotropic kinematic, these things, they are for cyclic loading, because if you are modeling steel under monotonic loading or cyclic loading, you have to define parameters differently. So that will also be discussed. will today discuss after this introduction, just steel beam under monotonic loading. Okay. Further, I'll show you how to apply torsion on a beam and do torsional analysis. We'll see the variation of shear stresses in different beams, maybe circular, square, rectangular, and for that we'll use coupling constraint. We will couple the reference point to the surface and apply torque on that. Rigid body constraint for sorry rigid body constraint for computing reaction forces, and these meshing techniques and path plotting, they'll be like there are x hex dominated wedge. These meshing techniques will be used for modeling circular beam, and path plotting will show you the variation of shear stresses along a path. So then we'll go to heat transfer analysis and thermal stress analysis. This is important because it has application in maybe concrete under fire, or simulating thermal behavior of viscoelastic materials. So we'll start with how heat transfer analysis is uh, performed in Abaqus. We simulate conduction, convection, and radiation, and also temperature boundary conditions are given here. We don't have to use the geometric boundary conditions for heat transfer analysis. Then I'll move for thermal stress analysis, for which we define this temperature field using another job file that will be demonstrated. Then we'll apply it to concrete and steel, and I'll show you how it causes damage to concrete. Then we go damage analysis, where we have a concrete sheet and a object falls on it. And we'll discuss that. There we'll use dynamic explicit solver. And obviously, when you have something in dynamic explicit and something is, you have to study impact problems, you have to define inertia, give mass to your falling object, or maybe to the whole system. Then I'll show you multiple collision problems. Suppose a ball or object falls on the sheet, then goes up, goes down, goes up, goes down, like that, in presence of gravity. So that will be also demonstrated in this module. So then this will be probably it about the modeling part, the modules, and we'll go for projects. So firstly, it is, we'll model a cantilever beam, maybe an elastic cantilever beam. So what we'll do is, we a similar problem, say a cantilever beam with a displacement applied at the tip, can be solved with solid elements, shell elements, beam elements, and plane stress elements. So we'll go there. In each of these elements, we'll go in the detail and compare the results and the computational efficiency in each case. So this will be first small project. Then we'll study the size effect of concrete. I'll use plane stress elements and concrete damage plasticity. Then what we'll do, we'll change the size of the element self similarly, and see how it affects the tensile shear, stress strain curve of concrete. So obviously I'll show you very good post processing, how you remove the edges or whatever, like how to extract data from a bucket. Those things will be demonstrated, and obviously these cost-static analysis will be used. This will be discussed before that also. Third project is the, we will model plane. I'm thinking in the previous course I modeled plain concrete walls, but now I'm thinking we can go with reinforced concrete walls also, and we'll subject it to pre-compression followed by in-plane loading, and then we'll study drift capacity, stiffnesses, and in-plane strength for different levels of pre-compression. It will affect the, if you have different levels of pre-compression, it will affect these three variables. Then we have the aspect ratio. Suppose we have a square wall with h by l, height to length ratio 1. Then you have something like slender wall, where height is greater, length is smaller, h by l ratio is greater than 1. And then you have squat wall, where length is greater than height. So we'll study for those three walls, and these parametric investigations can be carried out. Like obviously I'll show for something, rest is your assignment and you have to make a report out of it. Finally, if we get time, we'll go for reinforced. I have done this in previous batch. Hopefully we'll be able to do it, but it's an optional project. If we get time, we'll do this also, where we'll study bricks and mortar, and define them and simulate them as a plastic damage material using plastic concrete damage plasticity model. And then I'll also discuss cohesive zone modeling and the interface between brick and mortar. Following that, we'll go into the detail and validate our model against an experimental result. So there is an experimental wall which has been mm, experimented in maybe 1994 or something in Netherlands. So we'll model that wall in Abaqus, and I'll show you how our results uh, agree well with the experimental result. So this is probably it about the syllabus. So if you have any questions, you are welcome to ask. Anyone?
Maybe Ilham, like, raise your hand to asking something. So tell me, yeah.
You can also type your questions in the chat if you. Okay. Okay, I think there are no questions. So should we proceed towards the modeling part where I no question, it is clear. Okay. So should we proceed towards the modeling part where I discuss maybe steel beam? Mayank?
Yeah, I think there is no questions from anyone. So you can be starting the modeling portion. So if you have any questions, something. So at the end, we can be conducting the question answer session also. So you can be currently learning the modeling part from the Mr. Isam. At the end of this, we can be you can ask your questions and all. Okay.
Okay. So I'll maybe Mayank, you can stop presenting and I'll share the screen and discuss modeling steel. Ah, thank you. Okay. So okay. So this will be just about monotonic loading. And all of you may be knowing that steel at lower level of stresses it behaves as an elastic material and then plasticity comes in. So the behavior of elastic material in abacus is simulated using these three parameters: Young's modulus, slope of stress strain curve, right? Poisson's ratio and density. So up for lower level of stress, the behavior is like stress strain response is linear. Yes, everyone knows that, right? But when the stress exceeds the yield limit, I'll show you. See, I'll present and yeah, see what happens. So from A to B, the behavior is linear. It is elastic regime, right? Hooke's law is valid, and the response, stress strain response, it is linear. Once this elastic region or elastic regime is crossed, this B point is crossed, that is the yield limit is crossed in terms of stress, hardening is there, right? What does hardening mean? Hardening means that your elastic limit is now increased. Let me illustrate. Initial elastic limit was B, right? Then you went from B to C, and now you release the specimen. Okay. So what happens? Unloading will start, and it will start coming back to its own position. Suppose you have any square, and then you are maybe pulling it. If the stress strain response is in this region, the moment you release your load, the specimen will come back to its original position. So if it's like this, at this point you release your load, the unloading will start and stress strain curve will be like this. It will come back to its original position. But post when you cross this point, yield limit B, What happens if you unload? If you unload, it will also come back to its own position, but not exactly. It will unload like this. This CD line is the unloading line. How it is calculated? The slope is similar. The slope of this AB is equal to this CD, and then it comes to D, but not A. So there is some AD strain which is called plastic strain. So in this, once you cross the yield limit, if you unload, it won't come back to its own position, and there will be some irrecoverable plastic strain. Okay, but now if you load again, right? Initial limit was B, yield limit. Now if you load from D, the yield limit will be C. The yield limit will be C. So this is called hardening, the increase in the yield limit. Post that, there will be some softening, and this is the fracture point. I'll illustrate this in more detail. So firstly, let's talk about engineering and true stress strain. Okay, so up to now you must be using these relations. Stress equals to force here upon cross sectional area. Strain equals to change in dimension by initial dimension. But these are engineering stress and strain. Here you force by A naught. A naught is the initial area. U is change in dimension by the initial dimension. But when you elongate, say, your steel bar, what will happen? This lateral dimension L naught, it will increase, right, by U, and A naught, it will decrease because the volume has to be constant. So what will happen? A naught will decrease to A, and this L naught will increase to L. So you can't use these relations. Like, these relations will give you stress strain, but not in actual sense. So the true stress strain curve is given by, see how you calculate. True stress strain curve is given by these equations. So true strain equals to natural log of 1 plus engineering strain. True stress equals to engineering stress multiplied by 1 plus engineering strain. So this is how the stress strain curves look like. Initially, this is yield point, yield limit. Then there is hardening, and at this point, it's called necking. Necking means at this point the strain gets localized, and then it softens, and it's called rupture. So this is engineering stress strain curve. Okay. So this red was engineering, but for true stress strain curve, if you see this, true stress is less than engineering stress. Anyone with a basic knowledge of logarithms can say that, right? And sorry, true strain is less than engineering stress, engineering strain, because obviously when you use ln with someone, it decreases, right? But true stress, it is greater than engineering stress, because 1 plus engineering strain, 1 plus something, maybe 1.0001. So it is slightly higher. So you can also see that the stress strain response is, stress is greater here. Okay, but this relation is followed up to necking, these two equations, right? Before necking is the localization of strain, and hardening only in hardening region. Okay, after necking till rupture, how do you calculate true stress strain curve? Either you use linear variation simply. Okay, so you have, at the rupture, you have the load which you have applied in the experiment, and you have the area of cross section. You divide by that, the force and the area of cross section which you measure. So this will be your true strain, but at rupture, sorry, true stress at rupture. And your true strain is given by the similar, same equation, ln 1 plus engineering strain. But here it is at rupture, right? So you have this data already. You calculate this data by stress by this, strain by this, and you linearly join them. This is one method. Another method, but you say that I'll linearly join them, I'll draw tangent at this point. So you have this equation, sigma equals to a epsilon plus b, where a is sigma u true, that is true stress at necking, and b is given by this relation. Sigma u true is true stress at necking, and epsilon u true is true strain at necking. So this is one more method of how you approximate true stress strain curve after necking. Third is, it is given by a nonlinear relation. This is obviously taken from a research power law. This is a power law. You can see the terms. Function of sigma u true and epsilon u true is stress and strain, true stress and true strain at necking. And this epsilon is stress after necking. Okay, true stress after necking. This is non-linear relation. I'll obviously, when you'll enroll for the course, I'll share the research paper etc. is by Linz in 1996. The paper's name is, I think, stress strain curve of steel after necking, something like this. So this is taken from that. Then these three methods were discussed: how to compute true stress strain curve after necking. Then you have to, in Abacus, you have to input yield stress versus plastic strain. Okay. So yield stress, you already have the stress values, but how will you calculate plastic strain? True strain minus elastic strain. Elastic strain is this sigma epsilon y. So you have this, say, at this point, plastic strain equals to true strain minus this sigma epsilon y. Epsilon y is given by sigma y by E. So this data you put in Abacus, and you this is how it looks like: steel stress versus plastic strain, and you model the steel material. Okay. So now I'll quickly go to Abacus, and you can maybe get started. Okay. So we'll maybe do an elongation test of a rod. Okay. Steel rod. I can name it as rod. Okay. Well, I actually didn't discuss. I straight up. Okay. See. So name it as rod. Here we'll model it in 3D, and it is deformable. Okay. And solid element, obviously, and I'll use extrusion to construct the rod. Okay. Sorry. So I'll draw a circle here. This is how you click on this and draw a circle. I'll use some dimensions. The radius. Okay. How much should be the radius? Maybe 20 millimeter. Please note that Abacus does not have any system of units. So if you are using a specific system, then be consistent with it. Here I'm using millimeter for distance, and I'm using Newton for force, and obviously seconds for time. Then I'll click this. It will ask me how much depth should I extrude. So maybe I'll go for 2000. So this is your steel rod. Okay. Go to property. Now we have to create steel. Okay. You go like this. Firstly, you define oh, keep it as just I'll show you. You define density, that is 7800 kilogram per meter cube, right? But here I'm using instead of meter, I'm using millimeter, and kg is not my standard here, because when I'm using, see, let me show you. So my unit system is not MLT here, it is FLT. Okay. So kg per meter cube can be written like this: n equals to, like, F equals to ma, right? Then I can write kg as Newton per meter second square, right? This is kg and your meter cube. Obviously second is same, so just leave second. So you have Newton. If I convert these meters into millimeters, I'll get 10 raised to 12 millimeter cube. So I'll divide this by this value by, this is basic dimensions, 10 raised to 12. So it will be like 7.8 10 raised to minus 9. This is your density, right? Then you go with elasticity. So Young's modulus of steel is, how much is it? Can anyone tell me? 2E11 Pascal, right? But here my units are not Newton per meter square. It is Newton per millimeter square. That is megapascal. So I'll divide this by E raised power 6, like 10 raised to 6. So it'll be 2E5. Poisson ratio is zero point 0.3. So this is steel as thick, right? Steel as elastic. Steel as elastic. Okay. Then I'll maybe firstly I'll demonstrate elastic, then plastic. Okay. Then I'll create a section, name it as solid homogeneous. I'll just name it section 1, but you can name it as steel. Okay. And this material is used. Okay. This is now a section. Okay. To assign this section to this bar, which means that you have made a bar, right? But which bar is it? Is it concrete? Is it steel? Is it aluminum? What is it? So I have now assigned it. Now just this is the only section we have created. Now this is a steel bar. Then bring it to assembly. When you create an instance, this means you had a part. Now you are doing experiment in it on it. So you have transferred your part to the modeling space. Now I'll apply some loads, boundary conditions, and stuff. Okay. Going to step here, I'll use Abaqus standard, static general as of now. Obviously, later in the course, I'll discuss difference between the two. Okay. So I'll using this 1 second time period. And maybe this says that Abaqus standard doesn't, it can directly go and solve in one go, but sometimes it cannot. So it's better to start with point one. It will first start applying load, say be in linearly varying. So first point one, then point one again, then again point one, like that. You'll see, I'll show you. Just keep it as it is, fine as of now. No need to change it. Okay. So this is step. Then there is field output request. What do you want Abaqus to calculate for you? So it has mentioned a lot of things: stress, displacement, strain, everything. Okay. Obviously, you cannot have plastic equivalent strain or plastic strain or LE for elastic material. So it's okay. It'll show warnings, but you can also remove them. Anyways, let's keep them as it is because it's just a demonstration. So we'll go for load. Okay. So I'll fix this end and I'll apply a displacement here, some displacement. Okay. So let's fix this end first. If you go like this is box zoom view. Then you draw like this, it will zoom. Go for boundary condition. I'll fix it in the initial step. Select this one or this one, this one. Then you select the surface and fix everything. Okay. Now everything is fixed here. I want to apply a displacement here, and also I want to get the force displacement response. Okay. I want Abaqus to calculate force displacement response for me. So how do I do that? Okay. So I'll go to interaction and first create a reference point here. Okay. Now I'll use a constraint called rigid body constraint. Okay. So what it does is, I'll show you. I'll select this reference point and I'll maybe pin or tie. You can use both of them. These nodes. What happens is, now all these nodes will behave as a rigid body, and if I give, say, 1 millimeter displacement or 1 millimeter per second velocity to this RP, that will be transferred to all of these. Okay. First thing. Second, then I have to calculate force displacement response at each node, because FE analysis, what it does, it discretizes the system. At each element or at each node, there will be small reaction. This constraint sums up all the reaction and stores here. So I can get the force displacement response for this bar. Okay. Now this RP is here. Again, I'll define a displacement at this reference point. Okay. So I want to maybe subject it to tensile loading. Click done. just tensile loading. So all other degrees of freedom or constraint, this is 0. But U3, I need to give some displacement. So I'll start with 3 millimeter. Okay. So give a displacement of 3 millimeter. First thing. Another thing is I'll create a set. I'll name it as RP and continue and select this RP1. So a set is created corresponding to this RP1. Why? Because I need field output. I want Abacus to calculate force displacement response at this RP. So I'll go to step again in this field output, create a field output here in step 1. What I want for what? For set. Which set? RP. And what I want forces and I want displacements. Okay. So rest just keep it at it is every n increment means how many increments Abacus used. So at every n increments it will write the output. You can also use every x units of time. Total time is maybe 1 second. I can here write 0.1. So it will now write output after 0.1 seconds and then select OK. You can also use n increment, depends. So load, we have also applied the load maybe. Yes. Now go to mesh. We had, see, if you go to, sorry, in assembly here. So this is dependent. Okay. This is dependent. This is dependent because it is showing here make dependent. So when you go to mesh, you have to mesh part. So an assembly can be made of different parts, right? If you use independent, that it will mesh, it will discretize the whole assembly together. If you mesh by part, you can have, maybe you can discretize some parts as finer and some parts as coarser. So you can do like that. I'll explain it later, maybe when we have multiple parts. That's not an issue. Anyway, just see this part is 5.7 millimeter. Let's keep it as it is. And this is now discretized. So it is now divided into small elements. Like this is FEA, right? Okay. Following that, I'll go to job. I'll select maybe elastic with 3 millimeter displacement. Okay. It continue. Now I have to use parallelization because my PC is relatively good. So I'll use 6 processors to solve it. That will solve it quickly. I have 8. I'll use 6. Okay. Submit this. So this will be completed very fast. So this was elastic, right? I'll copy this module and name it as steel. Everything is same, plastic. Now I want to simulate steel as a plastic material. Here I just, in first module, I just defined 3 things, right? Density, Young's modulus, Poisson's ratio. But they are not sufficient to define plasticity. So how do I define plasticity? I'll show you. Same material is there. Maybe I rename it as plastic. Okay. Once I did it, these 2 things are as it is. You need to define here plasticity and plastic. As of now, you keep it isotropic. When we'll go for cyclic loading, we have to use combined hardening here and then use parameters. So I'll discuss them when we'll go reach there. So as of now, keep it isotropic. And as I said, you have to input yield stress versus plastic strain. This was where we stopped, right? Yield stress versus plastic strain. How do you calculate that? I already have the data. Okay, so here is the data. This one. Okay, so here it is. See. So this is engineering stress strain curve, right? This is from experiments. Okay. and this is the yield point, this value of stress. After this, hardening will start, right? Hardening will start, then there is necking, right? I discussed necking, strain localization. So at this stress, engineering stress, necking starts. And then we have used a linear, these are from experiments. We have used a linear variation from necking to rupture. So this is your engineering stress, engineering strain. You can convert it to true strain using this formula. Already discussed that. This is your engineering stress converted into true stress using this formula already discussed. Okay, now you have true stress strain curve. Up to necking, sorry, up to yield, there will be no plastic stress, right? Because if you unload, the specimen will come back to its own position. So at yielding, plastic strain will be zero, and this is your yield stress, right? This is your yield stress, that is true stress. Following that, you will calculate plastic strain using this equation, right? Using this equation. So the similar equation has been used here, and you will get the data, or you will get the plastic strain and yield stress data. So this data has to be inserted in Abaqus, right? So I have probably already defined this material in my material library. I click this. Hopefully this will be, yes, see. I already copied this and defined in my material library. Okay. Yield stress versus plastic strain. So all you have to do here is just change your section, change it to steel. Now it is defined as a plastic material. Rest, boundary condition, loads, everything is same, right? Only change here was changing the material of steel from elastic to plastic. Fine. Go to job, create job, meters, plastic, 3 millimeter. Why 3 millimeter? Because displacement given is 3 millimeter. Okay. Then maybe you will use 6 processors and submit. In the meantime, let's analyze this. So this is your how your stress distribution, von Mises stress looks like. You can also go for maximum principle, or you can maybe go for displacement U3. So this is the contour you have. But I'm more interested in force displacement response. So for that, I'll go tools, XY data, create. I'll use the field output because I had requested field output from Abaqus. And I'll select at node, unique nodal, and go for RF3 and spatial displacement U3. Okay. You can also select this, both of them are same. Then I'll go not pick from viewpoint is if you want to select any node here. What I want, I have already created a set RP. So go for that, plot. So this is linear, right? And it is expected of a elastic material. Does anyone have any questions till now? No? Anything? Okay. Let's analyze this one. This is the plastic material, right? Okay. Again, this is the displacement control, but I am more interested in force displacement response. So this is already selected. I'll go here. So this is also linear. Can anyone say why? What can be the reason that I model steel as elastic as well as plastic material, but the response is still linear? Anyone? It's a very simple answer for that. Someone has written no questions clear. Okay. Can any one of you say why did we get linear response for both, for modeling steel as elastic or plastic? Both in both the cases the response is linear. Why? Anyone? The reason is because the loading is small and your stress strain response is still in elastic region. How do we get non-linear response, or how will we get necking and, sorry, not necking, how will we get hardening? will just change from 3 to maybe 10. Okay, 10. So let's see what happens with 10 or maybe 15. And you can already although create here, or you can just copy. So my module is this and write 10 millimeter. Everything is same, just the name is different. And you submit it. Once it you submit the job, whatever you have defined material loads in your model, Abacus will use that, capture that, and then start working on that. So let's wait for the. See, I'll explain you this what is happening here. Okay, so I told you that we'll start with 0.1, right? Abacus started with 0.1. Then it again used 0.1, then again 0.1. So here, see at third, if you see the third row, there was a convergence issues. Okay, so Abacus could not continue with this time increment, so it had to decrease its time increment. So it decreased 0.25, it was fine, then it tried to increase again, convergence issues again decreased. So this is how it is. But when I here gave small displacement, there was no issue. See, in plasticity, see, no issue at all. It started with point 0.1, point 0.1, point 0.1, because I was asking output to write in point 0.1 intervals. It runs smoothly because displacement was small. There was no material non-linearity induced, and hence no convergence issues. See here also no convergence issues because it is elastic, so there's no point of convergence issues. But here it has some. Okay, so it's going slowly and steadily. Probably if I ask him to show me results up to time 0.29, we can see, just go field output, and this is already selected. Go to element nodes, node sets, RP. See, so it has bypassed the linear regime and it is now in hardening. Since it is in hardening, material non-linearity is there. There are convergence issues. So it will take some time to complete, but it will get completed. Okay, so this is the fundamental behavior difference. If I had given just steel elastic and given 10 millimeter distance displacement, it doesn't matter a lot, it will still complete job very fast because material is defined as elastic. But since I defined plasticity and I made sure the boundary conditions and the loading is such that the material is pulled enough so that the stress strain response goes in non-linear region. So that is why convergence issues are there. So this was the basics. Maybe in the course first you will model steel beam, then I'll show you the cyclic loading. For it, it's relatively different. We have to use parameters and we have to study this hardening, isotropic and kinematic hardening, everything. So that is obviously it takes an hour in class. So this is pretty much it. If you have any questions, you can ask. Anyone? Any questions about modeling or the course? Anything? Okay, no questions. Well, maybe stop presenting. And Mayank, you can now take over.
Yeah. Okay. Thank you so much, for these lessons, and hope everyone can enjoy it. So you can ask your questions if you have any in your mind, like regarding the training program, regarding the Abacus software or any other. Okay. Okay, no problem. We have our support WhatsApp number and email ID and all on our websites. So I will also be share the links of this training program on the chat box, so we can be check it the whole details on that. Also, there is a WhatsApp number to be available on the chat, so you can be connect on there and ask your any of the questions if you have. Okay. So thank you so much, everyone, to join us, and we can ending of this webinar now, and thank you so much for joining us. If you have any question or anything, you can be ask here, or you can be connect on